Hello students, a very big hi to all of you from my side. How are you all? I hope you are doing absolutely fine. So we were discussing about the periodic classification of the element, and in our previous chapter and in our previous lecture we have basically discussed about the Mendeleev's periodic table. Now moving out from all the chaos, the modern periodic table has been developed, which is accepted worldwide, and it provides a long term of the periodic table, because the periodic table that we are studied now is actually modern periodic table, and we know that this table is arranged according to the increasing number of atomic weights. So this description is basically given by Henry Moseley. So the all credits for this development goes to Henry Moseley. So let us learn about more things of the modern periodic table, and we will also learn some rule to remember the elements for the modern periodic table. So let's start modern periodic table. So we have earlier known that Henry Moseley says that the elements in the periodic table are the periodic function of their atomic number following physical and chemical properties. But how does this periodicity exist in the elements? Let us discuss now. Let us discuss about periodicity. So periodicity is actually when the elements in the periodic table is going to reoccur themselves at the regular interval of the time having same physical and chemical property. So that term is known as periodicity. And what will be the basic cause of periodicity? The periodicity is generally caused due to the presence of valence electrons in the outermost shell. So firstly, let us write about the definition of the periodicity. The elements in the periodic table starts reoccurring from a regular interval of time having resemblance in physical and chemical properties. Having resemblance in physical and chemical properties. So this is all about periodicity that we have discussed here, that element will reoccur itself after the regular interval of time. Now what will be the cause of that periodicity? So let us discuss the cause of periodicity. The cause of periodicity is basically the number of valence electron present in an atom. So the basic cause of periodicity will be number of valence electrons. So now we will see some of the elements, how the electrons are distributed in them and how they are following the rule of periodicity. So let us consider some of the elements here. So for this I am drawing a table over here. So let us have a look at this. We are drawing it to here. Here we will write the name of the elements. Here we will write the symbol of the element, and here we are going to write the electronic configuration. So firstly, here symbol, here I am writing the name of element, and here I am going to write the basic electronic configuration of that atom. Here we will write electronic configuration. So now this will be our basic consideration. Now consider the elements one by one. Suppose I am considering the element having symbol Li. Li means lithium. And what will be the atomic number for lithium? Hydrogen, helium, lithium, it is having an atomic number 3. Atomic numbers are, I am writing in the square brackets. So, if I write the electronic configuration of this kind of the atoms, the electronic configuration come out to be 2, 1. So, you can see that 2 electrons in the S shell and 1 electron in the P shell. Next, after lithium, we have our next element, that is sodium. Sodium is having an atomic number of 11. Sodium is having an atomic number of 11. So, I can write here, this metal is sodium. So, for the sodium, the electronic configuration will be 2, 8, 1. It means 2 electron in the S shell, 8 electrons in the P shell, and the remaining 1 electron will be present in the outermost shell. So, the electronic configuration will be 2, 8, 1. Now, moving to our third compound, lithium sodium. Let us consider potassium. Potassium is symbolized by the symbol K, having an atomic number 19. So, for the atomic number 19, that is potassium, we have this is potassium, and for that potassium, I can write the electronic configuration as 2, 8, 8, 1. It means 2 electrons, then 8 electrons, then 8 electrons, and the 1 electron in the outermost shell. So, this will be for lithium. This one is for and this one for potassium. Now, you can see that the electronic configuration is following the trend here, 2, 1, then 8, then 2, 8, 8, 1. Now, let us consider few more example of this category. So, I am drawing the half part of the table here because there is no such space for drawing this table here. So, let us draw the table here. Again, divide the table into 3 parts. Here I am going to write the symbol. After symbol, we have name of element. After name of element, we are going to write the electronic configuration. Now, let us consider few more elements here. So, let us consider few more elements here. Suppose the element I am considering here will be rubidium. So, the atomic number, here we can write the symbol as Rb, having atomic number 37. So, we can write the electronic configuration for such compound like 2, 8, 18, 8, 1. So, counting the number of electrons here, 8 plus 2, 10, 10 plus 8, 28, 28 plus 1, 29, and 29 plus 8 gives us 37. So, the number of electrons are completed here. Now, let us consider many more examples. Suppose I am considering cesium, having atomic number 55, and what is this element? This element is cesium. Then for cesium, we can write the electronic configuration as 2, 8, 18, 18, 8, 1. So, this will be the electronic configuration for cesium. So, let us check this electronic configuration. Up to this, we have counted 8 plus 2, 10, 10 plus 18, 28, 28 and 1, 29, 29, and after counting this 26, we will get 55 atomic number. So 55 atomic number is for cesium only. Now let us consider one more example here, that will be the last one. This is francium and it is having an atomic number 87. The name of the element is francium. So atomic number will going to follow the trend here like this: 2, 8, 18, 8, 8 and 2, 1. So the cycle will repeat itself like this. So this will be the electronic configuration for francium only. So let us look at this here. This table is now not following the trend. So we can say that these 8 electrons will not be accommodated in a shell again. So the last shell that accommodate maximum number of electrons will be 32 only. So the electronic configuration here will change to 32, 18, 8, 1. So this will be the electronic configuration. Now if you go on counting this number of elements, the number came out to be 87. So this will be the general electronic configuration that is following the trend in case of the periodicity. You can see here it is 2, 1, then 8 comes in the middle, then 8, 8, then between 8 and 8, 18 comes. Between 8 and 8, 18 and 18 will again going to repeat, and between that 18 and 18 again 32 is going to repeat. So the maximum electrons that can be filled in the shell will be 2, 8, 18 and 32. So you can observe this classification from this table. Now this is all about the periodicity and the cause of periodicity in the periodic table. Now let us consider the long form of the periodic table. So our next topic of discussion will be long form of periodic table. So let us discuss about the long form of periodic table. Now the modern periodic table is actually known as the long form of the periodic table, and all of the credit basically goes to Bohr, Bury and Henry. Why this model credit goes to this? Because the number of the valence electrons that are filled in an atom or in an electronic configuration is basically due to the Bohr's atomic model. The Bohr's arrangement of the electronic configuration has been basically used for the modern periodic table. So the major credit will goes to Bohr and Bury. So this long form of the periodic table is basically the periodic table which consists of the horizontal rows and vertical columns. The horizontal rows that we are considering are 7 in number, and the columns that we call groups are basically in 18 in number. So the modern periodic table is termed as a long form of the periodic table. So we can write here modern periodic table called long form of periodic table so its credit goes to the scientist known as, these are 3 scientists, Range, Bohr and Bury. So the main credit basically goes to three persons. Now this long form of the periodic table is based on the filling of electrons according to the Bohr's arrangement. So what we will done here, filling of electrons will be done according to Bohr's model. So this will be the next point of consideration in case of the long periodic table, and this period is basically divided into 7 rows and 18 groups. So this is all about the periodicity and the long form of the periodic table. Now let us move to the further descriptions of the periodic table. So now we will consider the characteristic about the groups or periods. So let us move to our next topic. Firstly, you can copy it from here, so we can proceed to the next one. So let us start now about the characteristics of the groups and periods in the periodic table. So now actually the modern periodic table has been starting now. So this is some of the basics about the modern periodic table that we have discussed here. So now our next topic will be making out of chaos, and this making out of chaos is nothing but it is a modern periodic table. Now, why I have used the term making out of the chaos? Because when different scientists tried their different attempts for the construction of the periodic table, like Daubernier law of octaves, then Mendeleev's periodic table, and finally moving out from all the chaos, we have generated a modern periodic table that we are studied now. So let us have a look at the modern periodic table. So this is our modern periodic table. I can rub from here so it might be visible to you. This is our modern periodic table, and you can easily see that it is a long form of the periodic table. This is actually a long form of the periodic table that we are seeing here. Now you can easily see that the 1, 2, 3, 4, 5, 6, 7. These 7 lines that are horizontal rows are known as periods, and the groups that are divided vertically, that is from counting from 1, this is 18th group. So the vertical columns are termed as groups. So let us discuss about some of the characteristics of both periods and groups. So our next topic will be general description about horizontal rows that are called periods. Now we will consider the points one by one by looking at this table only. So you can see that in this periodic table there are 7 horizontal rows, and these 7 horizontal rows, that is 1, 2, 3, 4, 5, 6, 7, are termed as periods. So the first point I can write here, horizontal rows are called periods. So the horizontal rows are known as periods, and there are 7 periods in the periodic table, that is in the modern periodic table. Second point we are considering here is 7 periods named as 1, 2, 3, 4, 5, 6, 7. These 7 periods can be named as 1, 2, 3, 4, 5, 6, 7. So this is the another point we are considering here. The 7 periods can be written like this. Now moving to our next property, it means each one will having a outermost shell present in their atom. So we can say that outermost shell will be available for each period. So the next point will be Each consists of outermost shell. So this is the next point of consideration, and you can easily see that the periodic table that is starting from periods having a general electronic configuration NS1. NS1 means in the S subshell one electron can be minimally filled. So the next point we are considering here, each will start with, each means each period is going to start with alkali metals. You can see that the first group that is present here are known as the alkali metals because these will have a property to form the bases easily. So each will start with alkali metal having NS1 electrons. So this is the next characteristic of the period. Now this table is starting from NS1. You can see here this table is starting from alkali metals. These are actually alkali metals. So we can see that this table has been starting from alkali metals having electronic configuration NS1, and moving along the periods we can see that this table has been ended to the 18th group element. This is our halogens. So these are halogens, these are actually noble gases. These are our noble gases, group 18 elements. These are noble gases. So you can see that the periods are actually starting from alkali metals and have been ended to the noble gases, and the noble gases have their outermost shell fully filled. So it is having a general electronic configuration NS2NP6. So we can say that starting with alkali metals, it ends with noble gases. It is ending with noble gases, and noble gases is having a general configuration NS2NP6. But you can note here there is one exception, that is helium. Helium is having a electronic configuration NS2. So helium will not be counted in the category of NS2NP6. So exception here will be, what is the exception here? The basic exception here will be helium. Helium is having an electronic configuration NS2, but apart from it all the other metals is having an electronic configuration that is NS2NP6. So these are some of the characteristics that I have written for the periods. Now we are having a 7 periods in the periodic table. So these will be divided into subshells. So the first period in the periodic table is known as a very small period because it basically consists of 2 elements only, that is hydrogen and helium only. So let us move to counting the number of shells or the subshells in the periodic table. But firstly, copy these characteristics from here.